Welcome to Microwave Engineering lecture series. In this lecture, we'll discuss about the quadrant wave transformer. Quadrant wave transformer. Consider a purely reactive circuit. For example, let us see this. This is the ZR, that is, it will be the ZL load impedance circuit, where Z0, the character is Z0, is the signal is transferred to the impedance transmission line of Z0. So this always for the ideally transmission line, the Z0 should be equal to the ZL. But in real time condition, we won't get this Z0 will not be equal to the ZL. So when it is not equal, some of the signals will get reflected back to the source, that is of Z0. So here to the source of ZS. So what we do is, to make the proper matching between the Z0 and ZL, we have to include the matching circuit between the Z0 and then ZL. So we know this law of reflection, that is of Z0. Already recall this equation, ZR minus Z0 divided by ZR plus Z0. Okay, so this equation you just recall it, and here this is the reflection plus Z0. So now this in between this mediator, the circuit, we are going to insert this matching impedance circuit, that we call this circuit is the quadrant wave circuit. So here the quadrant wave is a matching networking circuit or a transmission line used in the microwave or the RF engineering. So whenever we have to match between the source and the load, we have to insert the matching circuit between them. So between this source and the load, it is the main function is to match the impedance of transmission line segment to the other. So that is what written here, this facilitating the effective power transfer between the various radio frequency circuit. So the quadrant wave transformer idea is derived from the connection between the transmission line of physical length and the electrical length. So here the transmission line expression is a 90-degree in phase, that we'll see here. This quadrant wave we say as in lambda by 4 length, and this length should be the equal to this next length. So this quadrant wave transmission in lambda by 4, that's why we say as in lambda by 4 condition. So now what we do is, we insert this condition of ZL into Z0. So let us assume this as a Z1, which is the impedance matching, which is a quadrant wave transformer, the intermediate circuit. So this, if we multiply this, taking this Z1 here, that is what this R0 they have represented here. So what we do is, we recall this expression of transmission line characteristic impedance equation. Now we substitute this Z1 term, that is Z, also we can say as an R0 term, we substitute in this formula of tan beta S. So what, after substituting this ZL into Z0 in this equation, we get this matching circuit will get we'll have the proper matching between the transmitter and the. Now what we do is, by rearranging this expression, already we have seen this in previous lecture. So ZR by tan beta S, so beta is 2 pi S by lambda plus J of R0. So after switching the by multiplying this equation, so we get this quadrant wave length as S will become as lambda by 4. You substitute this, so we get a pi of tan of pi by 2, that is of 90-degree. So your ZS will be equal to your R0, that is of J of ZR plus R0 by J of ZR. So this equation we get here. So now this quadrant wave transformer, this all input impedance of the line is equal to the square root of R0 of the line divided by the load impedance. So already I have told that we have to multiply with ZS into ZR. So R0 is nothing but R0 square divided by ZR. So this is what the quadrant wave of a line may be thought as a transformer to match between. So this line will be the matching between this ZS into ZR. So this match can be obtained if the characteristic impedance R0 dash is, that is what I said as in Z1. Okay, so R0 is a mod of ZS into ZR. R0 is the matching section. So this line is the matching circuit between this ZS and ZR. Thanks for watching. In next lecture, we'll discuss about the Smith charts.